So picture this. You sit down at your desk, right? You open your laptop and you see, well, one computer, one keyboard, one screen, one operating system.
Yeah, it feels entirely singular, like a fixed one-to-one relationship between the physical machine and the software.
Exactly. But what if I told you that with a little bit of software sleight of hand, that one physical machine sitting right in front of you could actually be 5, 10, or even 50 completely independent computers?
All running at the exact same time and completely oblivious to one another. I mean, it really is the ultimate technological magic trick.
It's wild. And uncovering how that trick actually works is our mission for today's deep dive. We're taking an extensive look into virtualization, and we're using a really solid source for this Professor Messer's CompTIA plus certification training materials.
Right, which are excellent for this because we aren't just, skimming the surface here. We're getting right into the underlying architecture of how this stuff functions.
Yeah, so, okay, let's unpack this. Imagine you own a single plot of land. Normally, you build one massive single-story house that takes up the whole lot, right? You have one climate control system, one set of plumbing.
Makes sense.
But virtualization lets you take that exact same plot of land and build a skyscraper. And every single floor has a completely different climate, totally different architecture, completely different set of rules, yet they are all somehow sharing that exact same concrete foundation.
That's a great way to visualize it. And, the power of that architecture is that it forms the invisible backbone of our modern digital world.
Oh, absolutely.
Every single time you stream a movie or access a secure bank account or use basically any cloud application, you are relying on virtualized environments. So understanding this concept isn't just about passing some IT exam.
Right, it's bigger than that.
Exactly. It provides a lens into why our everyday technology is so fast, so scalable, and honestly surprisingly resilient to catastrophic failures.
Okay, so let's start by looking at that foundation. What are we actually separating when we talk about virtualization? Because normally when I buy a computer, the operating system, let's say Windows, it's married to the hardware, it expects to own everything.
Yeah, the operating system absolutely expects total dominance. It claims all the RAM, it schedules every single calculation on the processor, and it controls the network card.
It's greedy.
Very. But virtualization breaks that direct link. It intercepts those demands. So we take the CPU, the memory, the storage, and we slice them up. Then we present those slices to multiple, what we call guest operating systems.
Guest operating systems.
All right. And the brilliant part is that the guest operating system has absolutely no idea it's sharing. It is entirely convinced it has its own dedicated physical hardware.
I've actually seen this in action on a smaller scale. Like you have someone using a Mac as their primary computer, but they need to run a really specific piece of Windows software.
Right. Happens all the time.
Yeah, so they open a window on their Mac desktop, and suddenly Windows 11 is just booting up right there, functioning as a completely separate computer inside the Mac environment.
Yeah, so that is what we call host-based virtualization. You have your primary host OS, and you run a guest OS on top of it. But if we scale that up to an enterprise environment,
Like a massive corporate data center.
exactly. The approach changes drastically there. They aren't opening a little window on a desktop. They use a single, incredibly powerful server machine to run dozens of virtual machines or VMs simultaneously.
Wow.
And there's no graphical user interface. No one is moving a mouse across a home screen. It's just the silent workhorse processing massive amounts of data for multiple different systems all at once.
Okay, here's where I have to admit some confusion, though. The source notes mention that the foundational concept of this technology actually dates back to, 1967.
Yes, specifically on IBM mainframes.
Right. But back then, hardware was astronomically expensive. Right? So slicing it up to share among different departments made total sense. But today, hardware's relatively cheap. I mean, I can go to a big box store and buy a functioning laptop for $300.
Sure, you can.
So why go through the complex effort of building this digital skyscraper? Why not just buy 2 cheap laptops if you need 2 operating systems?
Well, cost is certainly still a factor at scale, but today, virtualization solves problems that simply throwing physical hardware at, well, it just cannot fix.
Like what?
It gives developers and IT professionals total control and safety, and it does this through a concept known as sandboxing.
A sandbox, meaning like an isolated environment where you can build things up and tear them down without making a mess everywhere else?
That's exactly it. Let's look at the mechanics of why a sandbox is so necessary. If a developer is writing experimental software, they simply cannot risk running that on their primary machine.
Because it might crash.
Worse than a crash. A severe bug in low-level code doesn't just freeze an app. It can corrupt the entire operating system, overwrite crucial system files, or cause a catastrophic kernel panic that renders the whole physical computer completely useless.
So you're risking the entire foundation of the skyscraper just to test the plumbing on one floor.
Exactly. But if they run that same experimental code inside a virtual machine, inside a sandbox, and the code goes rogue, the damage is fundamentally contained.
It can't escape the floor.
Right. The virtual machine itself might crash, it might blue screen, but the host computer remains perfectly unharmed. The developer simply deletes the corrupted virtual machine file and starts over.
And the Professor Messer materials highlight a feature that makes starting over feel like, honestly, actual time travel. Snapshots.
Oh, snapshots are a lifesaver.
Right. You can take a snapshot of a VM's exact state, every single file, every setting, every active process at any given moment. It feels exactly like saving your game right before walking into a massive boss fight.
That's a perfect analogy.
You walk in, you make a terrible mistake, and everything blows up. Instead of losing your entire computer or, spending hours reinstalling Windows, you just reload the save file. You are back exactly where you were 5 seconds ago.
Just think about the physical equivalent of that scenario. Rebuilding a crashed physical server. I mean, reinstalling the OS, configuring the network, restoring the data backups that can take a dedicated IT team days.
Days of downtime.
Yeah, but reverting a virtual machine to a snapshot, that takes mere seconds. That level of resilience completely changes how companies manage risk, and it also completely eliminates a headache of legacy support.
Oh yeah, this is a fascinating point in the deep dive. You might have a company running brand new hardware on Windows 11, but their entire payroll system relies on some custom-built application from a decade ago.
And it absolutely refuses to run on anything newer than Windows 10.
Exactly.
In the past, that company would have to keep an aging, vulnerable physical computer sitting in a closet somewhere just to run payroll.
Hoping it doesn't break.
Right. But now, they spin up a Windows 10 virtual machine on their modern servers. The old software gets the exact environment it demands, but it benefits from the speed and reliability of the modern hardware underneath.
Yeah, so smart.
And you can even take this across platforms. A developer could have a native Mac browser open, a Windows VM running an enterprise database, and a Linux VM handling a web server.
All on the same screen.
All on the same screen, all running natively without a single reboot.
Okay, which naturally leads me to ask, how do they not crash into each other? If I have a Mac, a Windows system, and a Linux system all running simultaneously, and they all decide they need maximum CPU power at the exact same millisecond, who plays traffic cop?
That is the big question.
Like, how do we prevent a catastrophic pileup?
We rely on the unsung hero of the entire virtualization ecosystem. It's a piece of software called the Virtual Machine Manager, though the industry standard term is the hypervisor.
The hypervisor. I gotta say, it sounds very intimidating, like a villain in a sci-fi movie.
Right, but its actual role is much more diplomatic. The hypervisor sits squarely between the physical hardware and the virtual machines.
Okay.
Remember earlier when we said an operating system expects total control over the processor? The hypervisor's job is to intercept those commands.
So it's the middleman.
Exactly. When a virtual machine says, hey, I need to write this data to the hard drive immediately, the hypervisor catches that request. It checks the available physical resources and allocates a specific slice of time and space to execute it.
While keeping it separated from the other VMs.
Right, all while maintaining strict boundaries.
But surely that interception process creates a massive bottleneck, doesn't it? Every single virtual machine we've talked about needs a fully installed, heavy guest operating system. Running 3 versions of Windows at once has to be an absolute nightmare for a computer's memory and processor.
It is a heavy load, yes.
I mean, my laptop starts sounding like a jet engine when I just had too many browser tabs open.
Well, the physical constraints of your hardware still apply. If you only have 16 gigabytes of physical RAM in your machine, the hypervisor cannot magically create more out of thin air.
Right, okay.
If you try to spin up 3 virtual machines and tell the hypervisor to give them each 8 gigabytes of RAM, the math fails and the system will crash. The power of the hypervisor is in its rigid enforcement of boundaries.
So you have to budget it out.
Precisely. You configure it to say VM number 1 gets a maximum of 4 gigabytes, VM number 2 gets 2 gigabytes. It will never allow a guest OS to pull more resources than it has been explicitly granted.
And the hardware itself actually has to be built to support this kind of rapid-fire switching, right?
It does. Processors had to evolve specifically to handle the overhead of virtualization. If you look at the specs for a modern Intel processor, you'll see a feature called Intel VT.
Which stands for Virtualization Technology.
Exactly. And AMD processors have a similar feature called AMD-V. These are actual hardware-level instructions physically built into the silicon. They allow the hypervisor to offload a lot of the complex routing directly to the processor, which vastly improves the efficiency of managing multiple operating systems.
Now, I want to get into how we actually install this traffic cop, because the CompTIA materials break hypervisors down into two very distinct architectures, Type 1 and Type 2.
Yeah, and the architecture you choose fundamentally depends on whether you are an everyday consumer or managing an enterprise data center. A Type 1 hypervisor is referred to as bare metal.
Bare metal.
Right. A common example would be a VMware ESXi or Microsoft Hyper-V.
Meaning it sits directly on the hardware. There is no underlying Windows or Mac operating system acting as a middleman.
Exactly. You take a brand new physical server, you turn it on, and the very first piece of software you install on that blank hard drive is the hypervisor itself.
So it is the operating system.
It acts as the primary OS, yeah. Because it communicates directly with the physical hardware, it is incredibly fast and efficient.
Whereas a Type 2 hypervisor is known as hosted. This would be software like VMware Workstation, Oracle VirtualBox, or Parallels.
Right, the consumer stuff.
Yeah, this is what I would use on my own computer. I already have Mac OS installed and running. I just download the Type 2 hypervisor and install it just like I would install a video editor or a web browser.
And because that Type 2 hypervisor sits on top of your existing operating system, it has to ask your Mac OS for permission every single time it wants to use the CPU or access the hard drive.
Oh, I see.
It adds a layer of translation, which makes it slightly less efficient than a bare metal setup. However, it provides the massive convenience of letting you check your emails, browse the web, and listen to music on your primary OS while running an isolated virtual machine in the background.
Okay, so we have the internal organs manage the memory, the processor, the storage. But a computer isn't much use if it can't talk to the outside world.
True.
If I have 3 virtual machines running on one physical laptop, how do they connect to the internet? Do they all just share my laptop's IP address and hope for the best?
Networking is actually where the hypervisor flexes some of its most complex logic. It essentially generates a virtual network switch entirely in software.
A virtual switch. Okay.
Yeah, you have complete control over how each VM interacts with the outside world, and there are 3 primary ways to configure it.
Let's walk through those configurations. The first one listed is a shared network address, which uses something called NAT.
NAT stands for Network Address Translation. In a shared setup, the hypervisor creates its own private, hidden network that your home Wi-Fi router knows absolutely nothing about.
So it's a secret network inside my laptop.
Basically. The hypervisor assigns private IP addresses to all your virtual machines. When a VM wants to load a web page, it sends that request to the hypervisor. The hypervisor translates the request, packages it up, and sends it out to the internet using your physical computer's single IP address.
It's like having a dedicated mailroom in our skyscraper.
Oh, I like that.
Yeah. The outside post office only knows the main street address of the building. The post office drops off all the mail at the front desk, and the internal mailroom sorts it out and delivers it to the specific floors. The outside world only ever sees one building.
That is a very clear way to visualize it. But there are scenarios where you don't want the virtual machine hidden behind a mailroom. You might need it to function exactly like an independent and physical computer sitting on your desk.
And that requires a bridge network.
Correct. With a bridge network, the hypervisor steps out of the way. Your home Wi-Fi router looks at the network and assumes you literally just walked into the room with a second laptop.
Oh, wow.
It assigns the virtual machine its own distinct IP address on your local network.
So the virtual machine can now communicate with my wireless printer, cast video to my smart TV, and interact with other devices on my network as if it were a physical piece of hardware.
Exactly. It's a full participant on the network.
Okay. And the last one.
Finally, you have the private address option. In this mode, you instruct the hypervisor to completely sever the virtual machine's connection to the outside world. It cannot reach the internet. It cannot see your local Wi-Fi network. It is entirely isolated.
Which brings us to the critical topic of security. Because if you are doing something inherently dangerous, like, say, analyzing a piece of malicious software to see how it works, you absolutely want that virtual machine on a private, isolated network.
100%.
But this leads to a specific vulnerability that seems to keep cybersecurity professionals awake at night. It's called VM escape.
Yeah, VM escape represents the ultimate nightmare scenario for cloud computing. We established earlier that sandboxing works because the environment is isolated.
Right.
But VM escape occurs when a piece of malware is sophisticated enough to realize it is trapped inside a virtual machine.
It knows it's in the matrix.
Exactly.
Yeah.
It actively scans the virtualization layer, finds a flaw in the hypervisor's code, and breaks out of the guest operating system to attack the hypervisor itself.
Let's bring back the skyscraper analogy.
Mm.
It's the equivalent of a sci-fi prison break. You've locked a highly dangerous entity in a windowless, isolated room on the 10th floor. You assume it's perfectly contained.
But it's not.
Right. The entity finds a microscopic crack in the concrete foundation, crawls into the building's central ventilation system, and suddenly it has unrestricted access to every single room on every single floor.
That's the terror of it. Once malware gains control of the hypervisor, it fundamentally owns the hardware. It can read the memory, intercept the network traffic, and infect every single virtual machine running on that physical server.
That is terrifying.
Now, while massive catastrophic breaches involving VM escape haven't decimated public cloud providers yet, it remains a high-priority threat that researchers are constantly identifying and patching against.
Which explains why the materials emphasize a strict set of best practices.
Yeah.
Just because a computer is virtual doesn't mean it's immune to traditional threats. You have to treat a virtual machine exactly like a physical one.
Absolutely.
You install firewalls, you run anti-malware software, you keep the operating system updated.
And one of the most common mistakes people make is treating virtual machines as disposable commodities. They will go to a random website and download a pre-built virtual machine that already has a Linux operating system and a bunch of specialized tools installed, thinking it saves them time.
Oh, I can see where this is going.
Yeah. Malware authors routinely upload infected pre-built VMs. When you boot that file up on your hypervisor, you are voluntarily handing the keys to a compromised machine. The rule is simple: always build your virtual machines from scratch using official operating system installation media.
Good advice. Okay, so we've explored the core mechanics, we've built the VMs, we've secured them, we've managed the networking, but all of this sets the stage for the next logical evolution.
Which is?
If we can successfully run an entire, fully functioning computer inside a window on our desktop, why do we even need the bulky physical desktop hardware in our office at all?
That realization led to the development of VDI, or Virtual Desktop Infrastructure. Sometimes it's called Desktop as a Service.
Okay.
VDI takes the virtual machine off your local laptop entirely and hosts it on a massive, powerful server in a centralized data center, often miles away.
So the physical computer sitting under my desk at work is essentially an empty shell.
We call it a thin client. It has minimal processing power. All you need is a monitor, a keyboard, a mouse, and a robust internet connection.
Really? That's it?
That's it. When you press a key, that input is sent across the network to the virtual machine in the data center. The data center processes the command, updates the operating system, and streams a live video feed of the screen back to your monitor.
It's conceptually identical to streaming a live video game, but instead you're streaming your entire Windows work environment. The CPU, the RAM, the hard drive storing all your files, none of this in the same building as you. You could accidentally drop your thin client in a lake, walk down the street to a public library, log into your VDI portal, and your desktop would appear exactly as you left it, with the same documents still open.
And with modern bandwidth, the latency is so low that most users never even realize their computer isn't in the room with them.
That's incredible.
However, whether we are talking about VDI in a data center or a Type 2 hypervisor on your laptop, we keep hitting the same fundamental bottleneck.
Which is?
The massive overhead of installing an entire operating system for every single virtual machine.
Right, because if you need to run 5 different isolated applications, you have to run 5 complete copies of Windows or Linux, which just devours memory and storage space.
Software engineers recognized this inefficiency and asked a pivotal question. Instead of virtualizing the hardware to support multiple heavy operating systems, what if we maintain just one underlying host operating system and we only virtualize the application itself?
And that breakthrough is application containerization, right?
Mm-hmm.
With Docker being the most prominent example. This fundamentally changes the scale of what we can do because these containers are incredibly lightweight.
To understand why they are so light, we have to talk about the kernel.
The kernel.
Yeah, the kernel is the core engine of an operating system. It's the specific code that translates software requests into physical hardware actions. A traditional virtual machine includes its own duplicate kernel, plus all the background services and drivers, which might take up 20 gigabytes of space and a full minute to boot up.
Right.
A container does not have its own kernel. It shares the kernel of the host operating system.
Oh.
Yeah, the container only holds the specific code, libraries, and dependencies required to run one single application.
So instead of a 20 gigabyte file, a container might only be 50 megabytes.
Hmm.
And instead of waiting a full minute for an OS to boot, the application spins up in a matter of milliseconds.
And that efficiency allows an enterprise to run hundreds, sometimes thousands, of isolated containers on the exact same physical hardware that could previously only support maybe 10 traditional virtual machines.
But there has to be a trade-off, right? Because containers rely entirely on the host operating system's kernel, you lose the ability to mix and match environments.
Correct. The shared kernel dictates the environment. If your host server is running a Linux kernel, it can only run Linux-based containers.
Oh.
You cannot run a Windows container on a Linux host because the Windows application won't know how to speak to a Linux kernel.
So to put this in perspective, a traditional virtual machine is like packing a massive RV for a road trip. You have your own kitchen, your own plumbing, your own climate control. You are totally self-sufficient and you can drive into any environment, but it takes a lot of fuel to move all that weight around.
I love that. And a container is like the ultimate hyper-efficient backpack. You can move incredibly fast, you can deploy instantly, and you carry almost no extra weight, but you can only pack clothes for one specific climate.
Right, you trade the rugged flexibility of the RV for unparalleled speed and scale.
And that speed is quite literally what powers the modern internet. When you open an app like Netflix, you aren't connecting to one massive server. You are interacting with thousands of tiny microcontainers spinning up to serve a video file, and then shutting down milliseconds later when the demand drops.
It really is a phenomenal progression. I mean, we've traced the journey from slicing up multi-million-dollar IBM mainframes in 1967 just to share processing time, to running Type 2 hypervisors on our laptops to test software safely.
It's been quite the evolution.
We've seen how VDI pulls the computer out of our office entirely, and how lightweight containers strip away the operating system to deliver applications in milliseconds. Virtualization has just proven to have the ultimate mechanism for maximizing resources and mitigating disaster.
It really forces a complete reevaluation of what a computer actually is. We have untethered the software from the physical box on your desk. Computing power is no longer a static object. It is a fluid, assignable resource.
And for you listening, this is highly relevant because it is the invisible engine of your daily routine. Whenever you access a cloud service, test a new app, or rely on a secure corporate network, virtualization is working behind the scenes, managing the traffic, and securing your data without you ever needing to see the complexity.
Which leaves us with a rather profound implication to consider. If virtual desktop infrastructure proves that our local hardware doesn't need to do the heavy processing,
Right.
and containerization proves that the underlying operating system can be made completely invisible to the application,
Oh, man, yeah.
are we approaching a point where the concept of the personal computer vanishes entirely, replaced by nothing but generic glass screens connecting us to a massive, infinitely scalable virtual brain in the cloud?